Welcome to Naradar Academy. In this video, I am going to discuss about analytic function. Now, I am going to explain what is an analytic function and I am going to explain you different forms of verifying whether a given function is analytic or not. In this video, I have given a bunch of problems for checking differentiability and analyticity of a given function. Okay, so by going through this video, we can get a clear idea of what an analytic function is. Okay, let's start with the definition. A single valued function w equal to f of z, which is defined in a domain D, is said to be analytic at a point A. That is, if z equal to A is a point in a domain, the function is said to be analytic if the function is differentiable at that point and also at all points in a neighborhood mod z minus a less than delta. Analyticity is a stronger condition than differentiability. Differentiable means differentiable only at that point. But for a function to be analytic at A, we need differentiability at that point as well as differentiability at all points in some neighborhood. Okay, this neighborhood may be taken as small as possible. But the condition is your function must be differentiable at all points in this neighborhood, not only at the given point but also at all points in the neighborhood. Okay, right. So this is the definition of an analytic function. So for checking whether the given function is analytic or not, we make use of one famous theorem that is given by Cauchy-Riemann, and the equations for verification are called Cauchy-Riemann equations. So these equations give necessary condition for checking differentiability, not for analyticity. They give you the condition for checking differentiability of a function. So what are the requirements for this theorem? We take a function f of z equal to u plus iv, and this is a differentiable function, and all its first order partial derivatives ux, uy, vx, vy all exist and they satisfy Cauchy-Riemann equations. Ux means differentiation of u with respect to x, uy means differentiation of u with respect to y, and vx means differentiation of v with respect to x, and vy means differentiation of v with respect to y. Okay, so what we are taking here, if a given function is differentiable, then all its partial derivatives exist and they satisfy these equation. What are the equation? Ux equal to vy and uy equal to minus vx. So differentiable implies these conditions are satisfied. Okay, this is necessary condition for differentiability. That means if your function is differentiable, definitely these equations will be satisfied. What is the other way? That is, what is the whether this is sufficient or not? No, these are not sufficient. If these equations are satisfied, we cannot say it is differentiable. Okay, understood? That is, differentiability implies these equations are satisfied, but when these equations are satisfied, we cannot say it is differentiable. One more condition has to be satisfied, that is given here, sufficient condition for differentiability. So if a function u plus iv is differentiable, and if that is the CR equations are satisfied as well as the partial derivatives ux, uy, vx, vy are all continuous. So only when these two conditions are satisfied we say differentiable. Can you understand? That is, differentiable implies these equations are satisfied. These equations are satisfied plus the partial derivatives are continuous. These two conditions together implies the function is differentiable. Okay, so this CR equation only we are going to make use for checking whether the given function is analytic or not. Now these CR equations can be written in different forms. Polar form means what? In terms of r and theta. U r equal to 1 by r into v theta and u theta equal to minus r into vr. So these are the CR equations in polar form. Okay, one more form is given here, one more form. What is that? Complex form of CR equations. See, f of z equal to u plus iv. Then the CR equations are given by fx equal to minus I into fy. What is fx? Differentiation of f with respect to x. This function, the function f is given, no, differentiate it with respect to x, and it is equal to minus I into fy. What is fy? Differentiation with respect to y. And another form is, suppose if you write f of z in terms of z and z bar. Okay, write all the real and imaginary parts in terms of z and z bar and differentiate the given function with respect to z bar. that is find dou f by dou z bar. If it is equal to 0, then that is called Cauchy-Riemann equation in alternate form. Okay, right. So these are the different forms for checking differentiability of a given complex valued function. While doing problems, you can have a better understanding of these equations. Now let me explain the problems one by one. This is the first problem. That is, we have to verify CR equations for all the given problems. See, f of z equal to z bar. So I have given you different forms of CR equations. No, you look at the problem and you can choose any one of the forms. So whichever is easier we can take. So here they have given the function in terms of z bar. So let me use this form. Okay. So if dou f by dou z bar equal to 0, then CR equations are satisfied. Otherwise not satisfied. Okay. That is differentiate f with respect to z bar. Here z bar is there, no. If you differentiate this with respect to z bar, the answer is 1. It is not equal to 0. So CR equations are not satisfied. So what can you say about this function? This function is not differentiable. Not satisfied means directly you can write not differentiable. Okay, then the next problem, f of z equal to real part of z. So here you can make use of any of the forms of CR equation. Now I am going to make use of dou f by dou z bar form. Okay, for that I am rewriting this in the form of z plus z bar by 2. Already I told you, no, in the previous video I have given introduction of complex numbers. In that one I have given you that real part of z can be written as z plus z bar by 2. Now you differentiate with respect to z bar. When you differentiate with respect to z bar, this z will become 0. Okay, 0 plus 1. 0 plus 1 is 1. 1 by 2. 1 by 2 is also not equal to 0. So CR equations are not satisfied. Okay, so not satisfied means what? It is not differentiable. The given function is not a differentiable function. Next problem, f of z equal to imaginary part of z bar. Here also I am going to make use of z bar. Okay, imaginary part of z can be written in z minus z bar by 2i. So differentiate with respect to z bar. So what happened? This z will become 0. This z bar will become minus 1. Minus 1 by 2i. It is also what? Not equal to 0. So that means what? CR equations are not satisfied. So not satisfied means what? The function is not differentiable. Okay. Next one. Next problem is f of z is equal to z. See, f of z equal to z. So I am going to make use of the same equation. I am going to check what is the value of dou f by dou z bar. So no z bar term is here, no. So if you differentiate, it will become 0. Right. So 0. So if you get 0, the CR equations are satisfied. CR equations are satisfied means what? It is differentiable. It is differentiable everywhere in the complex plane. Next one is, what about the analyticity? I told you already, if CR equations are satisfied, along with the condition, you have to check what you have to check. Continuity of the partial derivatives. Here you see z. It's a polynomial, no? All polynomials are continuous functions. Okay, so continuous. So along with the CR equation, we have continuity also. So together these two things implies what? The function is differentiable. The function is differentiable at all points in the complex plane. That means it is analytic. Again, it is analytic at all points in the complex plane. So it is called an entire function. Entire function means if a given function is analytic at all points in the complex plane, whatever complex number you take, if it is analytic there, that function is called an entire function. Can you understand? In all the previous problem, I have given that the CR equations are not satisfied. Whenever you get the CR equations are not satisfied, immediately you can write not differentiable. Okay, not satisfied means what? Not differentiable. But when you have satisfied, CR equations are satisfied, one more condition you have to check. What is that? Continuity of the derivatives. Continuity, for continuity and all, no need to do anything. Look at the function. From the function itself you can identify the continuity. Here it's a polynomial only, no. All polynomials are continuous, so continuous only. So what do we say? Differentiable. CR equation satisfied plus continuity is also there. So what do we say? It is differentiable. So where it is differentiable, that question arises, no. It is differentiable at all points because I didn't impose any condition here, no. At all points in the complex plane, dou f by dou z bar is 0 means at all points CR equations are satisfied. At all points the partial derivatives are continuous. So what do we say? At all points the function is analytic. So that means what? If it is analytic at all points in the complex plane, it is called as entire function. Okay, so this is an entire function. Next problem, f of z equal to minus z. Just I have changed the sign here. So dou f by dou z bar equal to 0. So CR equation satisfied. What about the continuity of the partial derivative? Yes, they are also continuous because we are having only polynomials, no? Polynomials are continuous functions only. So what CR equations along with continuity implies differentiability. Differentiability where? At which points of the complex plane? At all points. Okay. So at all points in the complex plane, CR equations are satisfied and the derivatives, partial derivatives are continuous. So what can we say? The function is analytic at all points in the complex plane. So when a given function is analytic at all points in the complex plane, that function is said to be an entire function. So this is also an entire function. Okay, understood? Then next problem, f of z equal to mod z square. See, mod z square. So this problem also I am going to write in terms of z bar. We know mod z square equal to z into z bar. So dou f by dou z bar equal to what? Z. Okay. So this is z, no. When will this become 0? This is equal to 0 only when z equal to 0. At all points this is not equal to 0. Let us discuss this case briefly. See, we are getting a dou f by dou z bar equal to z. Only this becomes 0 only when z equal to 0. At all other points not equal to 0. That means what? CR equations are satisfied only at the point z equal to 0. Okay. And then this is a polynomial only, no? Mod z square means what? X square plus y square. So polynomial means the partial derivatives are continuous. I am talking about only the z equal to 0 point. So at z equal to 0, CR equations are satisfied and the partial derivatives are continuous. So what can you say? Differentiable at z equal to 0. But you have to insist that differentiable only at z equal to 0. Why I am insisting that word only z equal to 0? Because only at the point z equal to 0, this will become 0. At the time only CR equations are satisfied. Okay, so what about the analyticity? Not analytic. Even at 0 it is not analytic because what is the condition required for analyticity? It has to be differentiable at that particular point, not only at that point, in its neighborhood also, at all points in the neighborhood. That means in at least one neighborhood of 0, this function has to be differentiable. But I have clearly stated here that the CR equations are satisfied only at the point z equal to 0. At any other point it is not equal to 0. That means at any other point the CR equations are not satisfied. So what do you say? This function is differentiable only at the point 0. That means it is not analytic at z equal to 0. Not only at 0, at all the points in the complex plane, this is not analytic. Okay, can you understand? Right. Next problem, f of z equal to z square. So f of z equal to z square. Again here I am going to make use of the same equation only. Let me differentiate with respect to z bar. It's equal to 0. So CR equations are satisfied. Again this is polynomial. So all the partial derivatives are continuous. So CR equation satisfied. All the first order partial derivatives are continuous. So that means what? Differentiable. Where it is differentiable? At all points in the complex plane. So obviously what can you write? Analytic. The function is analytic at all points in the complex plane. Therefore, it is also an entire function. Okay, right. Next one, f of z equal to c, where c is any constant. Okay, then dou f by dou z bar equal to 0 because constant, no, if you differentiate the constant, it will be automatically 0. So CR equations are satisfied at all points in the complex plane. So that means, and again, constant, no, every constant polynomial is also continuous. So CR equation satisfied, partial derivatives, CR equations are satisfied, partial derivatives are continuous. Together, these two conditions together imply differentiability. Differentiability where? At all points in the complex plane. That implies analytic at all points in the complex plane. That means this is also an entire function. Okay, then next problem, f of z equal to e power x into cos y minus I sin y. Okay, now I have a different type of problem. If you change everything in terms of z, it will be difficult for you to do the computation. Okay, so let me use another form of CR equation. This is f, no, f is given in terms of x and y. So let me take fy equal to minus ifx in this form. This is one of the CR equations form. No? In that form, I am going to check whether they are satisfied or not. You can verify CR equations in any one of the forms that I have given earlier. Okay, for simple calculations, you can take different forms for different equations. Now here differentiate this with respect to x. So when you differentiate with respect to x, these y terms are kept as constants. So keep these as constant. Differentiation of e power x is e power x alone. Okay, right. So this is fx. Next one is fy. When you differentiate with respect to y, this x term is kept as constant and differentiate only this. Differentiation of cos y is minus sin y minus I into differentiation of sin y is cos y. What is the that is CR equation form? Fy equal to minus I into fx. This is what we have to prove, no? So this is equal to, now you see, in this one, you take this minus I outside. So what happens? What happens? Minus I if you take outside, e power x into minus I sin y plus cos y, no? So CR equations are satisfied. Okay, right. So what we say, CR equations are satisfied, and this is exponential and trigonometric function. No? That is, trigonometric means what? Only cos and sine functions are there. Exponential, cos, sine, these are all continuous only. So when you differentiate, you are again getting sine, cos and exponential function. They are all continuous functions only. CR equations are satisfied, plus continuity of the first order derivatives imply this function is differentiable. Where it is differentiable? At all points, irrespective of any point in the complex plane, at all points it is differentiable. That means what? It is analytic at all points in the complex plane. So finally what we conclude, it is analytic at all points in the complex plane, hence it is an entire function. Okay, next problem is f of z equal to sin z. So here I am going to make use of dou f by dou z bar form. So there is no z bar, no, so automatically it is 0. So CR equations are satisfied. Satisfied where it is satisfied? At all points in the complex plane. Next one, sin is it only, no? Sine and cos are what? Continuous functions only. So the first order partial derivatives are continuous. So CR equations along with the continuous partial derivatives implies differentiable. Differentiable where? At all points in the complex plane. Therefore, it is analytic at all points in the complex plane. Hence, it is an entire function. Then next one is f of z equal to e power z. Again, dou f by dou z bar is equal to 0 because no z bar term is there, no. CR equations are satisfied. Where it is satisfied? At all points in the complex plane. Also, exponential function is a continuous function. Okay, so CR equation satisfied along with first order continuous partial derivatives implies differentiability at all points in the complex plane. Differentiability at all points implies analytic at all points. Therefore, this function is also an entire function. You can remember, see, every constant function is an entire function, exponential function is an entire function, every polynomial, this is a polynomial, no, for any positive powers. Polynomial is a entire function, sine is it and cos is it. Okay, sine and cos is it are also entire function, right? So, one more problem we will see. F of z is equal to xy plus iy. Now, for this one, I am going to make use of fx equal to minus ify. In that form, I am going to check. Differentiate with respect to x. What will you get? Y. Y alone. This will become 0. Here, differentiate with respect to y. So, it will be x plus I. Okay. These are not equal. No, fx is not equal to I into fy. So, CR equations are not satisfied. Not satisfied means not differentiable. Okay. Even at a single point, this is not satisfied. So, not differentiable. It is nowhere differentiable function. Next one, f of z is equal to x cube minus 3xy square plus I into 3x square y minus y cube. Now, here I am going to make use of the original format, that is ux equal to vy and uy equal to minus vx. In that form, I am going to check. U is the real part, x cube minus 3xy square. V is the imaginary part, 3x square y minus y cube. Differentiate with respect to x. So, 3x square minus 3y square. Here differentiate with respect to x. So 6xy, this will become 0. Now differentiate with respect to y. So 0 minus 6xy. Here with respect to y, 3x square minus 3y square. Now you compare ux. Ux is equal to vy. Equal, no? Right. Next one. Vx and uy differ by minus sign. Yes, correct. So CR equations are satisfied. CR equations are satisfied and all these first order partial derivatives are continuous because they are all only polynomials, no? They are all continuous. So CR equation satisfied, first order derivatives continuous implies differentiable. Differentiable at all points in the complex plane. Hence it is an analytic function in the at all points in the complex plane. Therefore, this is also an entire function. This is simply a polynomial, no? So it's an entire function only. Next one, f of z is equal to square root of r into cos theta by 2 plus I sin theta by 2. See, here we have to make use of polar form of CR equation. What is the real part? Root of r into cos theta by 2, and imaginary part is root of r into sin theta by 2. Differentiate u with respect to r. Differentiation, now when you differentiate with respect to r, this cos theta by 2 kept as constant. Square root of r, differentiation is 1 by 2 root r. Okay, differentiate with respect to theta. So root r is kept as constant. Differentiation of cos theta is minus sin theta by 2 into differentiation of this theta by 2 is 1 by 2. Okay, so minus 1 by 2 into root r into sin theta by 2. Now multiply this by 1 by r. 1 by r u theta, because in that form only we have CR equation. Okay, so 1 by r into u theta equal to, so when you divide it by r, this r and root r get cancelled and you will be getting minus 1 by 2 root r sin theta by 2. Next here, differentiate v with respect to r. So this r will become, root r will become 1 by 2 root r. Sin theta by 2 is constant. Next v theta, root r into differentiation of sin is cos theta by 2 into 1 by 2. So v theta is 1 by 2 root r into cos theta by 2. Okay, for verification you have to divide this by r. So 1 by r v theta equal to 1 by 2 root r cos theta by 2. What are CR equations in polar form? UR equal to 1 by r into v theta and VR equal to minus 1 by r into u theta. You check UR equal to 1 by r into v theta. Yes, both are equal. And VR equal to negative of this one. Yes, both are correct. So both the equations are satisfied. So CR equations are satisfied at all points in the complex plane. Along with that, the first order partial derivatives are continuous because they are only sine and cosine functions now, so they are continuous. So CR equation along with the continuity of the first order derivatives implies differentiability. Differentiability where? At all points in the complex plane. That means analytic at all points in the complex plane. Therefore, this is also an entire function. Okay, I hope you understood all the problems. Now let me give you some properties of analytic function. If f is equal to u plus iv is an analytic function in a region D, then whenever the real part is constant, the whole function is constant. Imaginary part is constant, whole function is constant. Modulus is constant, whole function is constant. If f of z and f of z, the whole complement are both analytic, then f of z is constant. And f of z and f of z bar are always simultaneously analytic. That is, both are analytic together or not. Okay, that's all. Thank you.